In this example problem, we have a conducting loop with 700 turns and a radius of 7 centimeters, and it's orientated in the xy plane. A magnetic field points in the positive z direction through the loop. So that means we have a loop, and the magnetic field is coming out of the page. Or drawn sideways, we have a loop, and the magnetic field is pointed in the positive z direction. The magnetic field strength changes with time by the function given. So we have a function for our magnetic field strength. If the resistance in the loop is 3.5 ohms, what is the induced current in the loop? And we have to remember here that induced EMF relates to induced current through Ohm's law. So ultimately we're trying to find V so that we can find I. So we're starting here with Faraday's law. And notice I dropped the minus sign. Often when we talk about these things, we're talking about just the magnitude. We don't worry about the negative sign. And I've written down Faraday's law, and I made a substitution here for the change in magnetic flux. So remember, magnetic flux is equal to BA cosine of phi. Our angle here, though, remember that the phi is the angle between normal to the plane of the loop and the direction of the magnetic field. Since they're both pointed in the positive z direction, phi is going to equal 0 degrees, and so the cosine of phi is equal to 1. So we're not worried about that in this case. So we're left with B times A. Now we have to decide what is changing. The area is not changing, but the magnetic field does change with respect to time. So that means that the change in magnetic flux is going to equal A times dB, which is the substitution I made up here. So I've now plugged in the 700 turns, so for N. I plugged in the area, so since it's a loop, it's going to be the area of a circle, so pi r squared. Remembering to convert my units appropriately. And then dB dt, so the derivative of the magnetic field strength in terms of time, is equal to this. So I've taken the first derivative with respect to time of the function for the magnetic field strength provided. I then begin reducing my algebra. So I've combined the numbers up front here to get this relationship here. And then I have subbed in for time in the function I got from taking the derivative of the magnetic field strength, which gives me this induced EMF. I can then plug into Ohm's law in order to get the induced current.